All right. Good afternoon, everyone. Thanks so much for coming. This is my great pleasure to introduce Gene Tkachenko. Gene is the CEO and founder of ETA Wireless, a Murata company. He holds a PhD in electrical engineering from Lehigh and is a graduate of MIT's executive program. From 1995 to 2013, he worked at Skyworks, leading development of several key technologies, SOI, FEMT for switches, HBT for power amplifiers, shipping billions of units and semiconductor devices, and many generations of smartphones. And he introduced industry's first 4G LTE modules. Gene was a part of two successful startup exits, with ETA devices acquired by Nokia in 2016 and ETA Wireless by Murata in 2021. Murata is a microsystems technology lab industry MIG partner, and we're pleased to present Gene for this special MTL seminar. Thank you.
Thank you. Thank you, Professor Jafari. Good afternoon. There was a wrong flyer sent out introducing me as expert on Raman scattering and biology. So if you're here for that, I apologize. I know nothing about that. I tried reading about it, but I really... So we'll be talking about digital envelope tracking and 6G today. So the outline today, I will briefly describe history of digital envelope tracking and ETA Wireless. I will present to you the problem associated with 6G, and it has to do with transmitter efficiency that we would be trying to address with digital envelope tracking. I will present the principle for the technology. I'll describe its benefits compared to state-of-the-art techniques used today. I'll show you some test results and then summarize. So let's start with the history. So this technology has actually been pioneered here by a couple of professors. Some of them you may know. Professor Dave Perot, he's still here, still teaching. He's still with our company as well. Him and Joel Dawson invented the technology about 10 years ago. The first company was started around 2011. It was called ETA Devices. We were privileged to be selected as a World Economic Forum Technology Pioneer in 2015. We were looking at this technology, digital envelope tracking, for base station transmitters, high power transmitters, as well as the mobile field. In 2016, Nokia came in and they acquired the company primarily with the interest in base station transmitters. We launched a new company called ETA Wireless with an emphasis on mobile communications. Among shareholders, we had State of Ventures, so that's also huge association with MIT in this local space, Intel Capital, and then Murata Manufacturing as well. We collaborated with several tier 1 chipset makers, and we were designed into several tier 1 chipsets. And in 2021, we became part of Murata, so we're quite happy, and we're, as a bigger team now, deploying this technology in several fields, where Murata is a big company, and we're addressing several fields with digital ET, which I'll present to you today. So we are still largely focused on developing solutions for RF power and efficiency in mobile and infrastructure applications. I'll be talking today about FR1, FR2, FR3 Wi-Fi applications. I'll describe what these are: frequency range 1, 2, and 3. We're continuing to innovate as ETA Wireless, as one of Murata companies. And we are privileged to have Murata as a partner in terms of scale for mass production, quality, yield, factories, reliability, sales channels. So it's really a perfect marriage for us. If you look at Murata as a company, it's known for breadth of its technologies. It's basically a gold standard for capacitors, inductors, modules, antenna modules. It has a lot of different technologies. We bring in a lot of complementary things as ETA Wireless. We're focused on digital envelope tracking. We have expertise in power management, digital pre-distortion, FPGA software, and IP licensing. So really very complementary set of skills that we develop together. Let me move on to the problem statement. So with 6G, and I'll start with this slide. And Taylor Swift is not the problem, but the problem is all of the people who like to transmit videos of her during concerts. And that's a problem for the network. That somehow it needs to be dealt with. And there's more of this type of demand. 29 terabytes of glitter moved through AT&T's network. And this is just one concert in Texas. This was the record. So somehow we need to deal with this data. People like sharing videos, doing it at the same time. It's a huge stress for the network. The network needs to run efficiently. The mobile devices need to run efficiently. And we're going to see a lot more of that. In terms of the mobile data trends, there are many exponential-looking charts like this describing how many exabytes, terabytes, gigabytes of data we consume and we're planning to consume. So exabyte is 1e to the 9 gigabytes. So today we're consuming over 200 exabytes per month, and the trend is going to continue. And 6G is going to be a large contributor to that. So with time, we need to somehow deal with this. Obviously, we need higher signal bandwidth and higher modulation schemes and modulation rates to be able to cope with all of this data that keeps coming. So let's look at this in the context of different wireless standards. If we look at the first set of, let me see, I have this. Yeah, I do have this pointer. So the first group, these are the core bands that you would have in your cell phones. These are the so-called FR1 bands. And they're sub-bands, low band, mid-high band, ultra-high band, subdividing this band. But typically, these are between 1 gigahertz and 7 gigahertz operating frequency. And the bandwidth in each one of these segments is up to 100 and 200 megahertz wide. So these are relatively modest but growing. If you look at the Wi-Fi, today Wi-Fi 6, 6E, 7, 8, 160 megahertz, 320 megahertz of bandwidth is required. These operate up to 7 gigahertz of operating frequency. 6G, these are some of the newer bands that are being discussed. I'll talk and present to you some data in these two ranges. The 6G FR3, so frequency range 3, low frequency is somewhere in the 7 to 8 gigahertz range, and FR3 high is somewhere in the 10 to 15 gigahertz range. These are the newer bands. They're still not completely deployed, but a lot of work is being done here as part of 6G. These would be most likely the first 6G bands that would be deployed and used. Here, the bandwidth of 200 and 400 megahertz, some of the wider bandwidth scenarios are being envisioned. Millimeter wave, or the 5G FR2, is deployed in some of the higher-end handsets, and that operates up to 800 megahertz of bandwidth. These are the millimeter wave frequencies in the 24 to 50 gigahertz range. There are also some future-looking, even wider bandwidth requirements that operate at higher frequencies, such as 802.11 ADAY and the 6G terahertz, where the bandwidth, signal bandwidth, is going to go even higher. So clearly, this is one way to address the requirements for wider data. But we need to be able to handle these wider bandwidth signals efficiently. All of these high bandwidth modulation, higher frequency, put more strain on the transmitter. Power amplifiers, PAs, need to work harder to deliver higher linearity, higher frequency, higher power, and higher bandwidth. So efficiency of these transmitters is extremely important.
Could you briefly mention which which bands and which bands are commercially available or present today, and which ones are expected in like 5 years and 10 years?
Yeah, so FR1 is commercially deployed today in all of the cell phones that you're using. Wi-Fi 6 and 6E is deployed. 7 is starting to get deployed. 5G FR2 is deployed in some of the high-end smartphones, and 6G is coming. It's not deployed. It's probably 3-4 years out. So that's kind of what you're kind of looking at the landscape today. So efficiency is important. Some of the techniques to deal with transmitter efficiency and power amplifier efficiency, analog envelope tracking, we'll talk about that later. It's a fundamentally lower bandwidth technique and can only cover a small fraction of these scenarios. So it works well up to 40 megahertz, but then extending it to 100 megahertz and beyond is very difficult. Door TPA is another way of operating it. Usually you have fixed supply operation and load modulation that is applied. That technique struggles with operating over wide frequency range. There's average power tracking. So average power tracking is operating basically at fixed voltage. So that is fundamentally inefficient, and you're losing efficiency there in that. And really, the digital envelope tracking is the only technique that can address these increasing band and bandwidth requirements. And that's what I'll be talking to you today. If we look at the mobile networks, so quoting one of the reports, it's a Next Generation Mobile Networks report, a lot rides on the power amplifier. So some of the data that's presented here, the base station consumes 73% of total operator network energy. And then the antenna unit consumes majority of power in the base station. And then the power amplifier is basically 60% of the antenna power consumption. If you multiply those numbers, really with digital envelope tracking technology, we can address almost 40% of total mobile operators' energy. So it's a huge number. And I'll be presenting to you the typical power savings with our digital tracking technology of 20 to 30%. So that alone, if implemented, can produce 12% reduction in the total mobile network energy. So these are huge numbers. This is from the mobile network perspective, not from the handset perspective, but from the standpoint of running the mobile network. So 5G deployment was more about throughput, so giving you these types of hundreds of megabits per second or gigabits per second speeds. 6G is viewed more about sustainability. It's a popular word these days, and if you look at sustainability report from companies like Ericsson, Nokia, everyone has their sustainability report. Basically, everyone is trying to run things more efficiently, and this applies to mobile networks. 6G will be more about efficiency, will be more about getting carbon out of it and getting to net zero, reducing the heat sink. If you can imagine, the base station is very heavy, and climbing up the tower is one of the most dangerous jobs in the world. So definitely making the base station lighter is one of the big tasks. But also it's more about reduced carbon and extracting efficiency and total cost of ownership drop per gigabyte. So all of these words you'll find in many of these sustainability reports. So again, back to how do we achieve these types of data rates, and how do we satisfy the requirements of the mobile networks today and 6G networks to come. If you look at cellular and Wi-Fi and other signals, you see the trends towards usage of more complex signals. These are high peak to average signals, going from QPSK modulation to 16 QAM, 64 QAM, 256 QAM. These are getting more complex signals and wider bandwidth, and also higher what's called modulation encoding scheme. In Wi-Fi 6 and 6E, enhanced, 6 enhanced, modulation encoding scheme 11 up to 1024 QAM is used, and then the extension of the Wi-Fi 7 puts that up to MCS 11 or 4K QAM type of signals. Also, so in addition to higher modulation encoding schemes, more spatial streams would be required to transmit more data. So all of these trends, in addition to higher frequency and bandwidth, put strain on the power amplifier. If you look at these types of signals in the time domain, this is one of the typical examples of such signal. You see infrequent high peaks, and the changes in the signal are occurring on the nanosecond type of grid, so they occur very quickly. These signals have high peak to average, and in order to have high data rate, you need to be able to capture these peaks. So if you look at this from the energy perspective, if you need to operate this so that these peaks are captured, and you need to supply the voltage to your transmitter that doesn't clip these peaks in order to have high fidelity, in order to have high linearity and transmit these rates without distortion. So there's a lot of associated energy waste in the areas where the peaks are not present. So that's clearly a problem. So how do you solve that? So you can just run this with high voltage and capture the high data rate. But however, efficiency would be low, and then the power transmitted, because you need to deliver this linearly, would be reduced. So this is one such scenario where you're running it with fixed supply and wasting all of this energy in yellow. The other way you can do it is you can clip these peaks and you can run at lower modulation. So you're losing information. Basically, you're not delivering 256 QAM type of signal, but you're going to a QPSK type of signal. This way, you can increase the power, you can increase the efficiency. However, you're dropping the data rate. So you're sort of clipping these peaks, but that's the way you can get larger power and larger range out of your transmitter. And then imagine if you can have a system that would give you ability to go from different discrete levels and then capture these peaks and then save all of this power. And this is what digital envelope tracking does. So I will explain how that works, the principle, and show you some data. But this is basically, we have these discrete levels, and we're jumping between them on the nanosecond grid, and we're able to both capture the high peaks and then operate the transmitter efficiently. So this way you can get the rate, you can get the power, you can get the efficiency. So let me move to describing the technology principle for digital envelope tracking. The principle of envelope tracking in general is basically you're changing the voltage as your signal goes through peaks and valleys. You can do that with analog envelope tracking, which is present in most of your smartphones today. This is sort of the red line. You're following it in an analog domain, and you're following it closely. And digital envelope tracking, as I mentioned, we create discrete levels. In the power converter, these discrete levels are created by this kind of supply generator. And then the supply modulator changes between these levels at the nanosecond grid. And that supplies the signal to your power amplifier. So what is the problem with analog envelope tracking? Analog envelope tracking has a high efficiency slow supply, and then the high frequency energy is delivered by this linear amplifier. It's inefficient, it's precise, but again, it's inefficient, and the combined efficiency of the converter is determined by these two components. As the bandwidth goes up, the linear amplifier has to work harder and harder and harder in order to follow the signal. So efficiency of the total converter drops. So this is the type of curve that you see for analog envelope tracking. And at some point in bandwidth, it doesn't make sense to use it anymore because you're wasting more energy in the linear amplifier. With digital ET, there is no inefficient part, such as error amplifier. We're generating discrete levels, and then we're basically jumping between them with a switcher. So all of the components of the system are very high efficiency. So you can imagine that you can track the signal. You can track the signal. You can decide when do you going to different levels, how long you're staying on different levels. So it's a completely flexible digital system that operates with high efficiency. So the advantage is you can go to very high bandwidth. You can capture these signals up to very wide bandwidth. And then also the efficiency of the converter is fundamentally much higher than the analog envelope tracker. So this is the core of the technology. You can also, from the supply that is present either in the base station system or in the handset system, you can have boost rails. You can go from lower voltage to higher voltage. You can boost power. So this type of power converter architecture is one of the sort of the crown jewels of the technology that has been created by the company. So as a result, you're operating with wider bandwidth. You're operating higher efficiency power converter. What is the problem? The problem is that you are jerking the power supply. You are creating, as you go from one discrete level to another, you are polluting the spectrum. So you need to correct for that spectrum. This is where the digital predistortion comes in. So this is the core part of the technology. With digital predistortion, you're cleaning the spectrum. You're cleaning receive band noise and out-of-band emissions. And this is another core part of the system. With analog envelope tracking, traditionally, digital predistortion is also used. However, you can envision system running without it. With digital envelope tracking, you do need this block. It's core part of the system. If you look at the diagram of the transmitter, so you would have your chipset, the modem, and RFIC. You would have several power amplifiers, depending on the system. So there are three core blocks of digital envelope tracking. One is the power converter. This is the typically a silicon IC, and it's integrated in the module with various capacitors, inductors. It's an IP block that does digital predistortion and tells the PMIC which levels to go to. This block resides with the chipset. It can be in FPGA or it can be in the partner's chipset. And also the third element is the software that's used for training and lab calibration. So again, three components. In terms of the power management module, these are developed per application to handle the power, to handle the number of outputs, to handle the voltage range. The digital predistortion block, again, this is kind of as part of that. It has the RTL that is provided to the transceiver and modem, and as well as the firmware. And then the deployment system is used for calibration, is used for automated measurements. It's used for system simulation. In addition, let me point out, in terms of the control of the signal, so we can have multiple PAs supported from the same power management unit, from the same PMIC. So you can run multiple PAs at the same time, 2, 3, 4. The control signal between the chipset and the PMIC is provided through digitally controlled levels. So these levels, it's an encoded interface that tells the PMIC, I need to go to this level, and then I need to change level and go to another level. I will describe this a little bit more in detail later. But that's the basic diagram and architecture. So there's, again, the power management, the digital predistortion piece, and then there's the software. In terms of the benefits, digital envelope tracking, or ET advanced, and I'll use the terms interchangeably here, you can think of that as delivering roughly 20–30% power savings compared to the baseline. I'll show you some of the data in various applications, but the baseline can be operating it with a fixed supply, operating it with average power tracking converter, operating it with the door TPA, or operating in with analog ET system. So we've done wide range of comparisons, and this is typically we save 20–30% power in various domains. Efficiency benefits extend to very wide bandwidth signal. As I described, this technique is applicable to very wide bandwidth. We can serve multiple channels of transmitters, multiple PAs operating at the same time. We can also serve very wide bandwidth. Some of these newer 6G signals extend to over 2 gigahertz of operating bandwidth. We can support that. I'll show you some of the examples. We can extend the throughput and range. We can go to higher modulation range for the same power. We can also extend the power, linear power of the transmitter, and by that extending the range of coverage. The technique also features simplified calibration and integration. I'll talk about that a bit more. Analog ET system, typically you have an amplifier, you have an analog ET tracker with a power inductor around that. You can have the shaping table, which essentially is integrated in the chipset, and then you have the DAC, which provides the information to the PMIC as to what the envelope does and when you need to change it. It's usually an analog interface. So this is typical for analog envelope tracking. If you look at the carrier aggregated scenarios where you have multiple transmitters operating at the same time, whether that's a CA, carrier aggregation, or MIMO, typically the system requires one PMIC per channel, so 3 PMICs here, 3 power inductors, 3 DACs, and then the shaping table. So it kind of multiplies the size of the solution. With digital ET, we can do that all with a single PMIC and a single power inductor. Because we generate discrete levels, we can leverage that kind of across multiple PAs. Also, we are replacing the analog interface with this digitally coupled line type of 2-wire interface per active channel. The advantage here is that this fully digital interface doesn't consume any power. So unlike in the analog envelope tracking, this interface is very noise prone, consumes power, and requires the DAC. We eliminate all of that. So we can save actually the area of the DACs or multiple DACs on the chipset. And then also we can go from multiple PMICs and multiple power inductors to a single PMIC and single power inductor. So this is the advantage of the digital ET system compared to analog ET in terms of its size. Additionally, power amplifiers can be located far away from the PMIC. This is one key advantage, specifically for the smartphone, where everything wants to sit close to the antenna. That space is very valuable, but you can't place everything there. So the advantage of digital ET is that we can handle large parasitic inductance and capacitance represented by these long lines, and we can still operate the system efficiently, which I'll show you some data to that extent. So if you look at the typical teardown of modern phone, you'll see a couple of these blocks, which are analog envelope tracking modules, and they're usually multiple. So in this case, there are 3 of them. One is operating the low band PA, one is operating mid-high band PA, and the third one for the ultra-high band PA. Again, everything is present in today's phone today, but you need 3 of them. The other thing is ultra-high band is the highest frequency. Typically, this type of PMIC needs to sit very close to the PA. Otherwise, there is the parasitic inductance and capacitance of the line, and analog ET systems struggles with that. So there are some severe physical constraints in the phone associated with this type of placement, in addition to the large size that this would occupy. I'll point out that some of these passive components, inductors and capacitors associated with it, are fairly large. So with digital ET, again, we can replace it with a single power management, with a single inductor, and reduce the size of the solution, and as well as provide additional constraint where the power management doesn't need to sit very close to the amplifier. So you can have much more flexibility in terms of routing the phone board. So another element here, I'll talk about the misalignment problem. So the principle is that when the envelope information arrives to the PA and RF, they need to be very precisely aligned. So the voltage follows the IQ envelope. If it's misaligned for some reason, then you have an error. In an analog ET case, you have an error at every point in time. It's cumulative. Whether that's a group delay in the filter, whether that's a part-to-part variation, whether that's something else, the system is needs to be very precise. Otherwise, you have an error, and your voltage and your RF signal is misaligned, and you have distortion as a result in the system. With digital envelope tracking, this problem is reduced because you only have an error at the vertical transitions. Everywhere else, you are still aligned. So the problem gets 10x better, roughly. It's a huge integration hassle in the cell phone. You need to design for millions of parts. You have variations in these parts. And the benefit of analog ET sometimes is reduced because of this dealing with this particular problem. So with digital ET, fundamentally, physics is much better. Physics is on your side. So I've shown these before. And capturing these infrequent peaks can be done with digital ET system. And in that way, you could actually operate the transistor beyond its static voltage limit. You could boost power for, let's say, 10 nanoseconds, and you can capture that peak, and you can increase instantaneous PSAT of your transistor. This way, in addition to providing a DC boost of the system, you can increase the power of the transmitter that operates linearly. So basically, you can extend the power of the transmitter. And by saving power, by going from, let's say, delivering 20–30% savings, you can also add more antenna elements. This is an example of the FR2 array, millimeter wave array, that's present in some of the cell phones today. But being able to put more antenna elements provides better patterns for transmission, and operating that with the same amount of heat dissipated in the phone is a huge deal, so your phone doesn't heat up. So these are a couple of additional benefits. Let me illustrate it in terms of some specific numbers obtained on a single element of such a millimeter wave array. So this element at 11 dBm of power, by saving 30% of DC power through digital envelope tracking, it results in roughly a watt of savings for the 8-element array present in the phone. So it's quite huge. So you can think of it as operating with high rate, but saving 30% of power. And this is where you can add extra elements to your beamformer. At high power, the nominal case is you operate a QPSK modulation with higher EVM. So you can only transmit this much data with the QPSK modulation. With digital envelope tracking, you can extend. You can go from QPSK to 64 QAM in this particular case. And you can extend your rate by roughly 2 to 3x. So think of transmitting 1 gigabyte of data at 18 dBm. In one case, it takes roughly 19 seconds. In the other case, it takes 6.4 seconds. So you can transmit 1/3 of the time and save power by that means. Basically, you are saving 67% of energy by transmitting faster. If you look at the coverage, whether that's an access point or small cell coverage for this room, for example, or for some office, typically you go from your unit that is transmitting. You can have very high data rate next to it, and then as you go far away, the data rate drops, and somewhere you lose coverage. With digital envelope tracking, you can extend the range of high data rate, but also you can extend the coverage of the low data rate scenario as well. So going to higher power and going to higher modulation encoding scheme. So that was the summary of the benefits of digital ET. Let me show you some of the test results in several segments. In terms of the application space, traditionally we've been looking at digital ET in the smartphone and wearable domain, and then these are various frequency ranges, FR1, the core cellular, FR3, the upcoming 6G, FR2 millimeter wave, and then Wi-Fi. And then also we have solutions in looking at the access point and the macro base station space. These are various PMIC solutions that I'm quoting here. They need to be optimized for a particular range of voltages and powers and active channels because they're all different for these application spaces. Let me start with the smartphone space and also bring up the test system that we typically use in the lab. This lab is using the FPGA, And without having a chipset, we can put our RTL that does digital predistortion and level selection onto the FPGA. We can run that in place of the chipset, and we can emulate the chipset. So typically, we would have a board with an amplifier or several amplifiers and our power management chip, and then the software that controls both the FPGA and this type of board to do this measurement. This is an example of a test board that replicates a set of power amplifiers present in modern smartphone. And the test cases are, in this particular case, we've looked at up to 200 megahertz of signal bandwidth. Recall my chart that this is the highest bandwidth that today's FR1 systems operate. And very high modulation encoding scheme, so 256 QAM, CPO FDM type of signal. So it's a very high peak to average signal. The test was done in the N77 band, that's a 3.5 gigahertz band, and Murata digital tracker was used to generate this data. So the typical power savings going from 20 megahertz bandwidth to up to 200 megahertz, which is the largest bandwidth available in that space, are on the 20 to 25% range, which saves about a watt of power in a smartphone, which is quite significant, quite substantial. This is comparing it to how the PA and the transmitter would not run normally. This is the same board, and the tracker is right here in the middle, and we would have a mid-high band amplifier, low band amplifier, and two ultra-high band amplifiers. These two ultra-high band amplifiers are identical. Typically, you would see many different amplifiers present in your modern smartphone. The only difference between these amplifiers is that they are separated by different distance. This path here to the lower amplifier is artificially made very long, 12 centimeters. So if you compare performance of these two amplifiers with digital envelope tracking system, and one is 2 centimeters away and the other one is 12 centimeters away, you can see that the next chart will show that the data is fairly similar for these two amplifiers. So that speaks to the flexibility of having it in different places in the smartphone. You can have one centrally placed power management unit in the smartphone, and you can run it to different antennas in different locations in the phone. The other complication here is we've added some extra capacitance just to illustrate how much capacitance the line between the PA and the PMIC can handle. So analog envelope tracking typically struggles even if the distance is over a centimeter away and if the capacitance is over 100 puff. The system has difficulties being stable and operating. So this is the summary of these two scenarios. So one set of data is for the ultra-high band PA that's 2 centimeters away, and the other one is 12 centimeters away from the power management unit. These 16 vectors typically are used to describe the power amplifier and a transmitter in the smartphone. There are different 5G signals, and they're different by modulation, QPSK to 256 QAM. They have inner resource blocks and outer resource blocks placed, and they're CPO FDM and DFT type of signals. So this set of 16 vectors completely describes the operation of the typical smartphone system. So, and you can see that the linearity measured as ACLR and EVM really hasn't moved for the PA that's 12 centimeters away. So you can still operate the system efficiently, linearly, and you can place your amplifier far away from the PMIC. So that basically is one of the big advantages of digital envelope tracking. The other one I've mentioned previously is the alignment between the RF path and the envelope path. So here, this data shows that 0 point is perfect alignment. This is as designed. However, the system was intentionally misaligned by several nanoseconds. So if you misalign it, adjacent channel linearity, adjacent channel power, and then EVM are behaved quite nicely over several nanoseconds. You are still in spec. And this type of misalignment is really not practical. It doesn't happen in real system. By comparison, analog envelope tracking needs to be aligned to tens of picoseconds. So it's an extremely sensitive system. So here we are misaligning the system, and it still operates pretty well. Let me show you some data in the 6G world. This is the operation of the amplifier from 6.5 to 8 gigahertz. So this is very wide bandwidth. This is still a prototype amplifier system, and we're saving about 20% of power for this scenario. This is early days of 6G. This is, again, operating over very wide bandwidth. Typically, a Doherty amplifier would struggle operating over this wide bandwidth. However, we are doing this with digital envelope tracking system and saving 20 to 25% of power. In the 6G FR3 high, which is the 10 to 15 gigahertz range, this particular set of measurements was done at 13 gigahertz. You see 4 amplifiers on this board supported by a single power management unit, a single PMIC, and then the signals, 100, 200, 300 megahertz wide bandwidth signals that can deliver those data rates that are required today. If we operate this type of system in the over-the-air system, so typically you need this type of chamber with the antenna and over-the-air measurements with these types of power amplifiers. This is the data. So we are 100, 200, 300 megahertz signals. We're saving up to 50% of power compared to operating this with fixed supply. The other thing is we can extend the power. We can go, typically the fixed supply reference system operates at 19.7 dBm. We can extend that linear range by 3 dB. So early days of 6G, however, showing really good potential. In the millimeter wave space, there are beamformers. I will kind of quickly glance through it, but here the core result here in the chart is that we are extending the power range by 3 dB compared to the baseline. This is the system that is operating with vertical and horizontal polarizations at 28 gigahertz, and we're able to train the system with a single element. So you can calibrate your digital predistortion with a single element of the array and apply it to the entire array, and it would still operate linearly. In the Wi-Fi space, a typical Wi-Fi access point has the chipset and several chains of MIMO, multi-in, multi-out, operating at 2 gigahertz, 5 gigahertz, 6 gigahertz. Sometimes it's up to 12 or even 16 transmitters that need to operate at the same time in order to deliver the high data rate. So in the access point, this means you need to use the heatsink, or you reduce the power, or the unit basically would need to be very large to accommodate this amount of heat. Digital envelope tracking, or ET Advanced, offers about 30% of savings based on this data, operating at up to 160 megahertz of bandwidth. So this is the typical Wi-Fi 6E type of case. So you can make your access point solution smaller. You can use less heat sinking. You can operate the system more reliably. And you can also extend the range of power and data rate coverage as well. So this is the typical spectrum for 1K QAM and then 160 megahertz bandwidth that's typical of Wi-Fi. In base stations, there are several scenarios. I'll quickly show one of the examples, 3.5 gigahertz, the so-called C-band radio. It uses 16 by 16 or 32 by 32 system, so 16 transmitters or 32 transmitters to deliver roughly 320 watts of power. Typically, the system uses gallium nitride PAs, so this is a higher voltage operation, 48 volts. So the power converter needs to be designed accordingly to handle this type of large voltage. So here, comparing to the baseline Doherty operation with digital predistortion, we're extending the efficiency from a little under 50% to 55% with digital envelope tracking while maintaining very good linearity. And moreover, we can run the system with 60% total system efficiency, including the tracker and the PA, which is really kind of getting into the record for this type of industry. Typically, PAs run less than 50% here. So you can envision base station PA savings with the use of digital envelope tracking. Moreover, the base station typically goes through various traffic patterns, so you can operate at peak traffic or lower traffic, and then these changes happen fairly quickly. There are several traffic models, and as we operate with digital envelope tracking where the voltage levels are present, you can easily navigate the system from operating peak voltages to lower voltages very quickly. Again, we are able to change the voltage on the nanosecond grid, so the savings that we deliver in this type of scenario are here over 20%. So in summary, digital envelope tracking delivers 20 to 30% savings. It can provide improved thermal profiles, extension of the power, extension of the data throughput and network performance. It is easier to integrate compared to analog envelope tracking in terms of the distance to the PA, in terms of the misalignment, in terms of the over-the-air beamformer scenarios. And it's a platform technology that applies to many of these cases, Wi-Fi, FR1, FR2, and is really the enabling technology for 6G that's coming. I want to leave you with maybe a couple of slides. These are borrowed from Professor Perot. Talks about the S-curve. So I'm not sure if you're familiar with the S-curve, but basically the progression of each technology follows this type of S-curve. Analog ET is actually fairly old technology that's been developed back in the 60s. And it has been broadly applied to various applications, including LTE transmitters. It's a fairly mature technology. It still benefits from device and material advances that are happening today, but does it slowly. It's actually fairly saturated. Because of the limitations that I covered, it's really not well positioned to handle wide bandwidth many transmit channels, the challenges that need to be addressed with 6G. So really it's kind of in saturation in terms of its S-curve. Digital ET is the new technology. It's a little over 10 years old. It's already outperforming analog envelope tracking in mobile applications and in all aspects. But it's still far from fundamental limits. We're still developing the technology. If you think about it, we are pushing the analog problem into the digital domain. We're using digital predistortion, the millions of gates in the chipset. This is where the problem will be solved more energy efficiently. In that area, we're still adding gates. We're going to hundreds of millions of gates. So signal processing is still evolving. Digital power converter technology is still evolving. So we're still kind of at the early stages of this technology. It would still be continuing to advance for decades. So really, in terms of its S-curve, we still haven't reached saturation. So that's why it's going to be here for decades. Thank you.
Thank you so much, Gene. This was an excellent presentation. Questions? Maybe I start with one. So if you might consider the demand in bandwidth, the mobile bandwidth, and then if you start putting it in perspective of the Moore's law, on the analog side, my knowledge is a little rusty, but let's say every 5 years, the power supply voltage for A2Ds drop by a factor of 2. And then on the battery side, every 10 years, it's about 30%, 40% better battery, right? So where do you think, and your talk was a really good example of this, but where do you think the fundamental focus and discovery needs to be to address the mobile bandwidth, and if there is any need for change of paradigm?
Yeah, it's a very good question. So the analog world is definitely not evolving at the same rate as the digital world. So if you ask the base station or an operator, they would say you can maybe improve power amplifier efficiency by 1% per year, at best. There are different voltage technologies, but typically you're stuck with gallium arsenide or gallium nitride for base stations, and there's so much you can do there. So definitely, in order to take advantage of the digital side that is progressing with the Moore's law and continues to go to 2, 3, sub 2 nanometer type of technologies. You need to do something like this. You need to transform the analog problem of the front-end efficiency into the digital domain and take advantage of all these gates, which is partially what we're doing here. We're taking advantage of the digital pre-distortion and navigate discrete levels with the smarts of the chipset that is throwing a lot of computational power and decision-making as to when do you change level, how long do you stay on the level, whether that's going to be an energy-efficient transition or not. That's really one way to do it. But in terms of making the front end more efficient, I mean, it's a very difficult problem. Industry has been struggling at whether that's a smartphone where your battery life is limited, or it's the base station that goes up there, whether that's solar operated. For example, there are some solar operated base stations, and you want to extract most out of that solar power that is delivered to the base station with the highest number of bits. So it's definitely every % change in improvement in efficiency is very difficult, very hard. So here with digital envelope tracking, it's relatively new technology, but we are talking about 20–30% power savings. This is really disruptive. This is really significant.
Oh, thank you for the wonderful talk. I was just curious, you showed that plot of like digital ET versus bandwidth. Do you know like what is like the carrier frequency limitation? So can you extend this technology to like 10 gigahertz, 100 gigahertz? I would imagine like DPD and the digital ET might get difficult at those really, really high carrier frequencies. Is that right?
Yeah, it's a very good question. So fundamentally, our part is frequency and voltage agnostic. You just need to design. It's a design parameter. Frequency is a design parameter, and power is a design parameter. So we've operated this up to millimeter waves and up to 800 megahertz of bandwidth. However, we need a good power amplifier at that frequency. So our technology is digital pre-distortion and power management that would work with the power amplifier and front end that would support that type of carrier frequency and that type of power. But fundamentally, there isn't a limitation. When things get to terahertz and 1 gigahertz plus bandwidth, you need to have more powerful chipsets as well. Typically, for digital pre-distortion, you need 3x analysis bandwidth to operate. So if you have a gigahertz of a signal, you need 3 gigahertz wide transmitter and receiver. So that's going to be challenging. And then operating a power amplifier tuned for terahertz frequency is a challenge in itself. The power management part is relatively easy. We can navigate that relatively easily. We know the particular vector, if that's going to go through peaks and valleys. When do we need to transition, and we can control that fairly easily. But the RF part operating at terahertz and with 1 gigahertz plus bandwidth is a challenge.
Is that like 3 gigahertz bandwidth on the digital ET side? Is that just limited by like the digital frequency of the digital electronics itself, or what makes that challenging?
So typically, in order to do the digital pre-distortion, you need to observe a larger part in order to correct the linearities and have the anti-distortion product injected in the RF. You need to observe wide. Typically, 2.5 to 3x is the minimum that's required. So to have an effective digital pre-distortion, you need to have that type of wide transmitter as well as the receiver. I haven't talked about the running the receiver. So different systems run the receiver periodically or open loop, or you can run it continuously. So you need to have also a very high quality receiver in order to receive that type of signal to correct the signal and pre-distort it.
Any other questions? Sure.
I'm curious, like with, when you go to 1024 and, that's a lot of bits. And how do you even go about designing all the different voltage levels? Is it like a machine learning approach, or do you have like some kind of analytical model, or do you just test every single bit and just figure out what is the optimal like pre-distortion and voltage level and go from there? Or like, can you talk a little bit about that?
Yeah, so there's a trade. So the starting point is what does your PA operate at, whether your PA is a 5-volt PA or 50-volt PA. So that's a starting point, or whether that's a silicon part that operates at 3 volts or lower, right? So you cannot exceed that. You cannot give your PA more than it can handle. Then there is a range, useful range for the PA, and that depends largely on how the power amplifier is designed. It depends on its AM to AM, the gain characteristics, the phase characteristics as well. If it's too nonlinear, then it's going to be difficult for digital predistortion. So there's also certain things that you can do more favorably in terms of amplifier design to help with this linearization problem. But then the selection of levels, obviously, you can have infinite number of levels, and then you're back to analog envelope tracking, right? So because you're following it almost continuously. And then too few levels, then maybe it's not enough saving. So there's always kind of a trade-off space. Also, the more levels you put in there, the larger the solution is going to get. So you have to also keep in mind the cost of the overall solution, because you're going to have more components in a larger space. So there's always a trade-off. But back to your AI question, we have fairly complex algorithms behind deciding whether we make a transition or not. With analog ET, you're always tracking. It's sort of a dumb system. With digital ET, you have an algorithm that you pre-train, whether you transition from level X to level X plus 1 or not. And that depends heavily on the power converter behavior, because you have the switching losses, resistive losses, and you may exceed the losses of the benefit that you're gaining. So maybe that's an unfavorable transition, you don't make it. So there's fairly complicated algorithm behind it, and we're, again, just scratching the surface with this. But this system kind of combines together the power management, the amplifier, the digital predistortion, all in one system, and then the algorithm behind it, the DPD, what type of equations you throw algorithmically at it also matters. So it's a very complicated system. Analog ET, the way to think about it, is just a power converter. Digital ET is really everything. It's the chipsets, the digital gates, it's the amplifier design, it's the whole system combined. So there's a lot of opportunity for this type of, you call it AI, and then we have some elements of genetic optimization actually when we look for the best optimum point, when we train the system. We have fairly complex algorithms running behind it. So yeah,
Thank you.
Very good question.
Do you see any additional opportunity by, for example, applying this very fast responding power management circuits in other areas? For example, I don't know, microprocessors, the other places where you also want to adjust the power supply in dynamic.
Yeah, absolutely. So you can operate that system even without digital predistortion as the fast average power tracking converter. You can apply that to application processors. You can apply that to these types of scenarios, in whether that's a Wi-Fi or base station where traffic pattern changes very quickly, and you need to react on a sub-slot level, or we can do it on a sub-nanosecond, or actually nanosecond precision. So definitely, you can think of this. Let's say applications processors is one such area. So we are focused mostly on RF, but the core technology is applicable to many different spaces. Professor Perot is doing work, so he's the father of these digital converters in many different places, plasma and other, completely unrelated to RF. So, yeah.
Okay, thank you so much. Thanks our wonderful speaker.
Thanks a lot.